Right now, at this exact moment, liquid nitrogen is seeping upward through cracks in a glacier the size of Texas and Oklahoma combined, nearly 6 billion kilometers from the sun. On a world so cold, its surface sits at minus 230 degrees Celsius. On a world smaller than Earth's moon. On a world that, by every rule of physics we established decades ago, should be a dead, frozen rock with no internal heat left to do anything at all, something is moving. That world is Pluto. And in August 2026, a team led by Alan Stern, the principal investigator of the New Horizons mission, published a peer-reviewed study in the Planetary Science Journal confirming something that should not be possible. Liquid is actively rising through Pluto's famous heart-shaped glacier right now. Not millions of years ago, not in some distant geological past, but now. And the question nobody had properly answered, because everyone assumed the answer was obvious, turns out to be one of the strangest puzzles in the entire solar system. What is keeping Pluto warm? The answer involves a nuclear reaction that has been running continuously for 4.5 billion years, inside a world we dismissed as dead for most of the time we have known about it. And the full picture is far stranger and far more alive than anything the textbooks ever described. Let us start with the problem, because understanding why this discovery is so shocking requires understanding just how impossible it should be. Pluto sits an average of 5.9 billion kilometers from the sun. At that distance, sunlight is roughly 1,000 times weaker than it is here on Earth. The surface temperature hovers around minus 230 degrees Celsius. The atmosphere is so thin, you could not breathe it even if you were somehow immune to the cold. Pluto itself is smaller than Earth's moon, with a diameter of only about 2,300 kilometers. A body that small, sitting that far from any heat source, should have lost virtually all of its internal warmth within the first billion years of its existence. This is not speculation. It is basic, well-established physics. Small objects have a high surface area relative to their volume, which means they radiate heat into space far faster than larger bodies can. This is precisely why our own moon is geologically dead. It is why Mars, despite being much larger than Pluto, is far less active than Earth. The smaller the world, the faster it cools, and the sooner it should become a static, frozen, lifeless ball of rock and ice. By that logic, by every model scientist trusted for decades, Pluto should have been completely inert, no liquid water, no geological activity, no surprises. That was the consensus for most of the 20th century and into the 21st. And then, in July 2015, NASA's New Horizons spacecraft flew past Pluto for the first time in human history, and everything the consensus predicted turned out to be spectacularly, humblingly, wonderfully wrong. The images New Horizons sent back showed mountains of water standing several kilometers tall. They showed nitrogen glaciers actively flowing across the surface, like slow-motion rivers of ice. They showed dunes of methane ice shaped by wind in an atmosphere so thin that scientists were not even sure it could move solid material at all. They showed cryovolcanoes, ice volcanoes, structures like Wright Mons standing 4 kilometers tall with a gaping depression at its summit, and Piccard Mons rising even higher at 7 kilometers. One of the largest volcanic structures relative to its world's size found anywhere in the solar system. And most stunning of all, they showed Tomball Regio, the now famous heart-shaped feature made of bright nitrogen ice, with its western lobe called Sputnik Planitia, standing out as one of the youngest, smoothest, most geologically active surfaces found anywhere in the outer solar system. A member of the New Horizons team, planetary scientist Jeff Moore, said after the flyby that Pluto is every bit as complex as Mars. That is not a throwaway comparison. Mars has volcanoes, canyons, ancient riverbeds and dust storms, and a geological history spanning billions of years. To call a tiny frozen world at the edge of the solar system equally complex is an extraordinary claim. But the images backed it up completely. So what is producing all of this activity? What is keeping this small, distant world warm enough to maintain liquid beneath its surface, warm enough to drive glacial flow, warm enough to feed active cryovolcanoes and produce some of the youngest terrain in the entire Kuiper Belt? The answer is radioactive decay. And understanding exactly how it works inside Pluto is what makes this story so remarkable. Pluto's heat comes from the decay of radioactive elements, particularly potassium-40, buried deep within the rocks at its core. Radioactive decay is the process by which unstable atomic nuclei release energy as they slowly transform into more stable configurations. Potassium-40, along with uranium-238 and thorium-232, were incorporated into Pluto when it first formed roughly 4.5 billion years ago, from the same swirling cloud of gas and dust that gave birth to the entire solar system. These isotopes decay incredibly slowly. The half-life of potassium-40 is 1.25 billion years. The half-life of uranium-238 is 4.47 billion years. These are not fast explosive reactions. They are a slow, steady, continuous trickle of nuclear energy that has been running without interruption since before the Earth itself existed in its current form. The key to making this work lies in Pluto's internal structure. Scientists believe Pluto is differentiated, meaning that early in its history, as the young world heated up, denser materials like rock sank toward the center, while lighter materials like ice rose toward the surface. This left Pluto with a rocky core surrounded by thick layers of water ice, with nitrogen, methane, and carbon monoxide ices forming the outermost surface we actually see through a telescope. The rocky core is where the radioactive elements are concentrated, and the heat they continuously generate radiates outward into the surrounding ice, which acts as a thick, insulating blanket, trapping that warmth for billions of years. The primary source keeping Pluto's suspected subsurface ocean liquid is this same radioactive decay happening deep in its rocky interior. And that ocean is not pure water. It is believed to be a mixture of water and ammonia, with ammonia acting as a natural antifreeze. Pure water freezes at 0 degrees Celsius, but water mixed with ammonia can remain liquid at temperatures far below that, in some mixtures, dropping to nearly minus 100 degrees Celsius before freezing solid. This ammonia antifreeze effect means that even as Pluto's core loses heat slowly over billions of years, its subsurface ocean has a much wider temperature window in which it can remain liquid. The combination of continuous radioactive heating and ammonia antifreeze is what has kept liquid water beneath Pluto's icy crust for billions of years, quietly, invisibly, completely unknown to us until New Horizons arrived. But the story does not stop there. And this is where the newest research becomes genuinely startling. In August 2026, Alan Stern and his team published what may be the most significant Pluto-related findings since the original New Horizons flyby itself. They found direct evidence that liquid nitrogen is actively seeping upward through cracks in Sputnik Planitia, the heart-shaped glacier right now, or recently enough that the surface features it produced remain geologically fresh. The study, led by researchers at the Southwest Research Institute, focused on dark, thin, linear features and broader diffuse patches found along the northern edge of Sputnik Planitia. The team compared these features directly to dark wetting patterns observed on Earth's own Greenland ice sheet, where liquid water emerges from beneath the ice and visibly darkens the surface as it spreads. The match, according to the researchers, was striking. Their modeling showed that liquid nitrogen could realistically travel upward through small conduits, similar in concept to lava tubes or geyser channels, and remain liquid long enough to reach the surface and create these same dark wetting patterns on the nitrogen glacier above. Based on modeling of surface turnover rates, the surface of Sputnik Planitia is estimated to be less than 1 million years old, which, by planetary standards, is essentially yesterday. That means the features the team identified must have formed extremely recently, placing this liquid nitrogen activity firmly in Pluto's present, not its ancient past. Alan Stern himself said that Pluto never stops surprising scientists, and that this particular result certainly does exactly that. Beyond simply confirming that liquid has recently existed on Pluto's surface, the finding suggests something even more remarkable, a genuinely time-variable feature. In other words, Pluto is not just geologically active in some slow general sense. It appears to have surface features that are actively changing on timescales that, in geological terms, are almost instantaneous. The mechanism driving this is called basal melting, meaning the very bottom of the glacier is being melted from below by heat rising up through the ice. And that heat traces back to the exact same source that has been producing it for 4.5 billion years, the radioactive decay churning quietly inside Pluto's rocky core. Follow the chain of events for a moment and really sit with how extraordinary it is. Deep inside Pluto, radioactive isotopes of potassium, uranium, and thorium are decaying, releasing nuclear energy as heat, just as they have since before our own planet existed. That heat warms the rocky core. The warmth radiates outward into the ammonia-rich ocean layer above it, keeping that ocean liquid despite the crushing cold surrounding it. The heat continues rising into the base of the massive nitrogen glacier, sitting kilometers thick above the ocean. At that boundary, the pressure and residual warmth are enough to melt solid nitrogen ice into liquid nitrogen. That liquid nitrogen is slightly less dense than the solid ice surrounding it, so it rises, finding cracks and fractures within the glacier, seeping upward through those tiny conduits, the way water might slowly travel through porous rock. And when it finally reaches the surface, it wets the nitrogen ice, creating the exact dark linear patterns that Alan Stern and his team have now identified and matched to processes we already understand here on Earth. This is a continuous, active, ongoing geological process powered entirely by nuclear energy, taking place on a world nearly 6 billion kilometers from the nearest star. Now consider the cryovolcanoes as further proof of just how alive this world really is. Right Mons stands 4 kilometers tall and spans roughly 150 kilometers across, a massive structure built primarily from water ice with a deep central depression closely resembling a volcanic caldera here on Earth. The very existence of a structure this large strongly suggests that Pluto's internal structure allows for either far greater heat retention or simply far more heat overall than scientists ever anticipated before New Horizons arrived. Picard Mons is even larger, rising a full 7 kilometers above the surrounding terrain. Both structures share a telling characteristic, an unusually low number of impact craters. In planetary science, a low crater count is one of the most reliable indicators of geological youth, because a surface that has been recently resurfaced simply has not had enough time for new craters to accumulate on top of it. In March 2025, a separate study published in the Planetary Science Journal by researchers at NASA's Jet Propulsion Laboratory identified a possible new cryovolcano, informally referred to as Kiladze Caldera, located northeast of Sputnik Planitia. Unlike the primarily methane-rich terrain surrounding it, this feature and its immediate surroundings show a distinct water ice signature, carrying traces of ammoniated compounds, closely matching 2 other confirmed cryovolcanic sites already identified elsewhere on Pluto. That ammoniated water ice signature functions almost like a fingerprint left behind by material that originated deep inside the world, evidence that a slurry of water, ammonia, and liquid ice erupted onto the surface from below and then froze in place. A literal geological calling card from Pluto's internal nuclear furnace. What makes all of this even more significant is what it implies for the rest of the outer solar system. The region beyond Neptune, the vast Kuiper Belt, was long assumed to be a graveyard of frozen, inert, leftover material from the solar system's formation, objects too small, too cold, and too far from the sun to ever be geologically interesting again. That assumption is now collapsing under the weight of new evidence. Findings of internal heat activity on other Kuiper Belt objects like Eris and Makemake, combined with the confirmed geysers erupting from Neptune's large moon, Triton, and now this direct evidence of active basal melting and liquid nitrogen seepage on Pluto together build a coherent and compelling case that the outer solar system is far less dead than its brutal temperatures might suggest. The same ancient nuclear engine powering Pluto may be quietly powering an entire population of small, icy worlds scattered across the outer solar system, worlds we have barely begun to study in any real detail. All of this scientific momentum has fed directly into a very public, very human moment. In April 2026, a 10-year-old girl named Kaylee Polkinghorn from Tampa, Florida, wrote a letter to NASA asking them to make Pluto a planet again. She listed her reasons carefully and included multiple polite pleases, for good measure. Within hours, NASA Administrator Jared Isaacman personally replied on April 9, 2026, telling her that NASA was genuinely looking into it. This was far more than a courteous response to a child's letter. Isaacman later told a Senate Appropriations Committee hearing on April 28, 2026, that he is very much in the camp of making Pluto a planet again, and confirmed that NASA is actively preparing formal papers on the subject. Papers they intend to bring forward to the broader scientific community to reopen this exact discussion. The argument is not rooted in nostalgia, it is rooted in evidence. The International Astronomical Union's 2006 criteria required a planet to orbit the Sun, to have enough mass to become roughly spherical under its own gravity, and to have cleared its orbital neighborhood of other debris. Pluto satisfies the first two conditions easily. It fails only the third, because the Kuiper Belt is crowded with other large icy bodies sharing similar orbital space. But a growing number of planetary scientists now argue that this specific requirement was always a strange and somewhat arbitrary line to draw, since even Earth shares its orbital neighborhood with roughly 10,000 nearby asteroids. And Jupiter shares its path with over 100,000 Trojan asteroids. By a strict, literal reading of that same rule, even Earth and Jupiter have not fully cleared their own orbital neighborhoods either. The deeper issue is that the original 2006 vote was contentious from the very start, decided by only a small fraction of the International Astronomical Union's full membership on the final day of a conference, and it has never fully sat well within the broader scientific community since. A growing number of researchers now argue that geophysical complexity, internal structure, active geological processes, a genuine atmosphere, and a dynamic, changing surface represent a far more scientifically meaningful definition of what a planet actually is, compared to a narrow rule about orbital mechanics. And by that far more meaningful definition, Pluto is unambiguously a planet. It has a fully layered internal structure complete with a rocky core, a likely subsurface liquid ocean, and multiple distinct ice layers. It has active, ongoing geology driven entirely by internal nuclear heat. It has a genuine atmosphere that visibly expands and contracts with the seasons. It has towering mountains, flowing glaciers, wind-formed dunes, and active cryovolcanoes. It even has a moon, Charon, so proportionally large relative to Pluto itself, that the two bodies orbit a shared point, an empty space between them, a configuration completely unique anywhere else in our solar system. As of now, the International Astronomical Union has not changed Pluto's 2006 classification, but the simple fact that a sitting NASA administrator is formally pushing to reopen this exact debate, citing direct scientific evidence gathered from New Horizons, means this is no longer a matter of sentiment or nostalgia. It has become an active, ongoing scientific and institutional question. There is something fitting about the timing of all of this. The August 2026 discovery of liquid nitrogen actively seeping through Pluto's surface is simply the latest in a long, steady chain of findings that have systematically dismantled every single assumption originally used to justify Pluto's demotion back in 2006. The assumption that it was geologically dead. Wrong. The assumption that it had no subsurface liquid whatsoever. Wrong. The assumption that it was nothing more than a simple, cold, inert rock. Wrong. The assumption that meaningful complex geology belongs only to the larger inner planets. Also wrong. What New Horizons discovered during its brief flyby in 2015, and what scientists continue to uncover today as they reanalyze that same data more than a decade later, is a small, distant world that has earned every ounce of its complexity through the most ancient and reliable energy source known in the universe, the slow, patient decay of radioactive nuclei. A nuclear reaction that began before the solar system had even fully formed into its current shape, that has been running continuously for 4.5 billion years without pause, and that right now, at this very moment, is still melting the base of a nitrogen glacier nearly 6 billion kilometers from the sun, and pushing liquid upward through cracks in the ice to a world we once dismissed as too small, too cold, and too far away to ever be interesting again. Pluto is not a frozen rock. Pluto is a nuclear, heated, ocean-bearing, cryovolcanic, atmosphere-breathing world, one that scientists are still uncovering brand new evidence about in 2026 alone. It is geologically as complex as Mars. It is scientifically as fascinating as Europa. And it is keeping itself warm using a nuclear reaction that will not stop for billions of years to come. Whether or not the International Astronomical Union ultimately agrees with NASA's own administrator, the data itself has already answered the far more important question. Pluto is alive. Its own internal nuclear reaction decided that 4.5 billion years ago, and after everything scientists have now confirmed, it clearly has not changed its mind. If this story genuinely fascinated you, if the idea of a tiny frozen world quietly running its own private nuclear reactor for 4.5 billion years gave you chills, then do not scroll past without hitting that subscribe button. Because this channel exists specifically to bring you real, verified, mind-expanding discoveries happening at the very edge of human knowledge. Drop a like on this video right now if you believe Pluto deserves to be called a planet again. And let us know in the comments whether you think NASA will actually succeed in convincing the International Astronomical Union to reverse its 2006 decision. Share this video with anyone you know who grew up believing Pluto was a planet, because after everything you just learned, they deserve to hear this story too.